Hello friends, hope you are fine in this pandemic situation. In this lecture, today's lecture, we learn approximation methods applicable in quantum mechanics. So first of all, we learn what is approximation method and when or whether we apply application methods. So you know that only few problems have exact solutions. That means most of the problems have no exact solutions. Further, if any problem has exact solution, then it is not so easy or quick enough to get exact solution of that problem. So let us take some examples from our daily lives as well as from classical mechanics and mathematics, and then we gradually shift to quantum mechanics. So let us take an example from our daily life. Okay. So say in market you buy a fish at 850 rupees per kg. So let us write, say 850 rupees per kg, and the weight of the fish is say 700 gram, so that is 0.700 kg. So what is its price? Its price is, say I write P0 is 850 into, so it becomes 595 rupees. So this calculation is very easy to calculate mentally. Okay. Now I say if the weight of this fish becomes say like this, so I write W0, so I write say 704 gram, so that means 0 kg. So what will be its price? Its price will be E is equal to 850 into 0.704 kg. Therefore, so the multiplication is little difficult for seller as well as for you. So to ease the calculation, what seller do? Seller considers this as simple 0.70, and he takes, if he neglects this part 004, see he takes only 595. So approximate price is 595, which is exactly solvable. So to be more specific, so I write this one as like this. Say I write this one as 850 into 0.700 plus 0.004. So it becomes 850 into 0.7 plus 850 into 0.004. So it becomes 595. 00 plus 3.0. So seller losses this amount. Okay. So what fraction, what percentage he lost? I can calculate this one. Say P. So del P by P is equal to P minus P0 by P. So it becomes almost only 0.6%. If you calculate, you can find this. Okay, only 0.6%. So in this case, approximation is very good because seller lost only 0.6%. After when he rebates this part, when this rebates this, so he losses only 0.6%. So in analytical expression, if I write this one price of this fish, so in analytically I can write P. Say this is A term, I can write this A, and I write this weight as B. So A into B. Say I write A into B0 plus del B. I write exactly solvable part as this. This I write B0, and this I can write. So this means A B0 plus A into del B. So this part is exactly solvable or exactly determined, can be exactly solvable, and this is the correction. This is the correction. Okay. So we see that exactly solvable part is very greater than correction term. So in this case, it is approximation holds good, very good. Okay, so now I take, say, okay, so now price of fish is, say, I take A as this, I write A0. Okay, so this I write A as rupees 852 per kg, and weight is which I write weight as same 700 gram, means 0.704 kg. Okay, so what is its price? Its price is P is 852 into 0.704. So I can subdivide each part of this one like this: 8 plus 2 into 0.700 plus 0.004. So I write 850 into 0.7 plus 850 into 0.004 plus 2 into 0.007 plus 2 into 0.004. So what is becomes? This is 595, and this is becomes 4.80, and this part only 008. Okay, so this is one. So this is exactly solvable part. This is first correction, and this is second correction. So I see that exactly solvable part is very greater than first corrections, and then first correction is very greater than second corrections. So if the seller approximates or did not consider this part 2 rupees 2, and if he did not consider the weight of this fish, this part, so he will get only 595. So by doing this, what he loses, if I calculate what fractions he loses, so I can calculate this one as del P by P is equal to P minus P0 by P equal to around say 0.8% only. So in this case, approximation holds very good. This is big. That means that if he debates this part and this part, the price he demand is not far away from the exact value, exact price. Okay, so analytically, if I write this part again, so if I write price is A into B, this means that A0 plus del A into B0 plus del B, then A0 B0 plus A0 del B plus B0 del A plus del A del B del B. So this is the exactly solvable part, or dominating part, exactly solvable, and this part is first correction, and this part is second correction. So okay, so this is second correction. So we found that exactly solvable part is far greater than the correction term. Okay, so this part del A and del B, we may call this is disturbance in the price or in the weight of the fish. So del A, del B can be called disturbance. So in this place we can coin a term. The perturbation. So this disturbance may be called perturbation because in quantum mechanics this disturbance or fluctuation are called perturbation. So when perturbation is very less than the dominating part, then we can apply approximation method. Or if the perturbation part is not less than the dominating part, then we cannot apply approximation. For example, again we go back to that example. If we write that 8 mass weight price of the fish rate is like this, 852. So if I write this one, 800 plus 52 and 07 plus 0.04, and if you make it 0, or if the seller rebate this mass 52, then it simply becomes 560. So in this case, del P by P is around 7%. So in this case, we cannot apply approximation methods, or approximation methods loses its validity. So we call from this simple example that approximation method holds very good when perturbation or fluctuation becomes smaller then the exactly solvable part becomes negligible or very much smaller than the exactly solvable part. Okay. Now we shift our attention to classical mechanics and mathematics. So first of all I take an example from classical mechanics. So we know that Earth revolves around Sun due to gravitational attraction of Sun on Earth, and you know that the orbit of the Sun is elliptic, keeping Sun at one of its focus. Okay, but you know that to know the exact orbit or exact path of Earth around Sun, we have to also consider the gravitational force of other solar planets as well as other celestial bodies. So in that case, the motion of Earth, or you may call this problem, is a many-body problem, which is popularly known as n-body problem. N-body problem. Okay. So the motion of Earth, revolution of Earth around the Sun becomes a n-body problem. Okay. But what we learn in our school physics, in our graduation, what we do there? Actually we do some approximation. What we do? Since Sun is heavily mass compared to Earth and other solar planets, as well as other celestial bodies are very much distance away from our solar system. So we can consider the effect of other solar planets as well as extraterrestrial bodies as perturbation, and hence we can neglect their effects on motion of Earth. In that case, we consider only the two-body problem between Sun and Earth, and in that case, motion of Earth around Sun is governed by, you know, that Kepler's law and Newtonian laws of gravitation. Similarly, the motion of Moon around Earth, to know the exact orbit of Moon, we have to also consider the gravitational force of Sun and other planets, etc. What we usually do, neglecting their effect. So, and most intriguing example of this approximation methods, you know, that discovery of Neptune. Uranus, you know that Uranus discovered in 1781, but the actual path of, but there is some discrepancies or irregularities in the actual path, actual observed path of Uranus and predicted Keplerian orbit of Uranus. So these discrepancies or irregularities in the path of, in the motion of Uranus can only be explained if we consider presence of another twin planet near Uranus, and this effect this effect can perturb the motion or orbit of Uranus. And fortunately, 60 years after discovery of Uranus, Neptune was first theoretically discovered and then experimentally discovered. So next we take an example from simple harmonic motion. So let us take an example of a simple pendulum. So you know that expression or equation, simple pendulum equation is this one. Sin theta. We expand sin theta in Taylor series expansion. G by E theta minus theta cube by 3 factorial plus theta to the power 5 factorial minus this one. Okay. This. Okay. So when theta is small, or when theta is less than 4 degree, so in that case we can neglect this part, theta to the power cube or greater than theta to the power cube, theta to the power 5, etc. So this part gives you the harmonic term. You know, this is harmonic term and this part is anharmonic term. So anharmonic term or perturbation. I think this is, you know, this part is perturbation or disturbance in theta. When theta is shifts from the lower value, say 4 degree. So in that case, if we consider the full expressions of sin theta, time period will be t equal to t0 into 1 plus summation over n so time period becomes t equal to t0 1 plus summation some sin theta dependent part to the power n, where n equal to 1, 2, 3, etc. Okay. If theta is small, then t equal to simply t0. So this is twice pi g by L. And if theta is greater than 4 degree, then you have to consider this full part. Okay. So when theta is small, less than 4 degree, so what is the error or what is the percentage if we do not consider the full expressions? So if you calculate, we see that t minus t0 by t0 is only 0.3%. Only it becomes only 0.3%. Okay, so that means that t equal to 1.003 t0. Okay, so in this case, so our approximation holds very good. So this is another example of approximation or perturbation in the exactly solvable value or part. So let us take an example from mathematics, from matrix. So let us write a matrix. A0 is 1, 0, 0, 2. So you can determine its eigenvalues. Eigenfunctions. So it has two eigenvalues, one is 1, another is 2, and its eigenfunctions is 1, 0, and this eigenfunctions is 0, 1. 0, 1 you can calculate, and it is very easy to calculate these eigenvalues and eigenfunctions. Okay, so now if this matrix, if we add some off-diagonal part to this matrix, then I can write this matrix as A equal to 1 epsilon 2. And for example, for this time I consider epsilon is very less than 1. So you can directly diagonalize this matrix to get its eigenvalues and eigenfunctions, or you can subdivide this matrix in two parts. One is exactly solvable and another is its perturbation, when we call it this perturbation when epsilon is very less than 1. So we can diagonalize this matrix A either by direct full diagonalization or applying perturbation method, provided perturbation here epsilon or off diagonal part is much less than diagonal values from which we get unperturbed eigenvalues and eigenfunctions. Okay, this to this point we come later. This I tell just to give an example of perturbation or approximation method. So from these examples, one I take from our daily life and another from classical mechanics and matrix. So what we conclude about approximation methods? So we can conclude that approximation method is applicable. Approximation method is applicable under two conditions. First, application method is applicable. Approximation method is applicable when the problem is sufficiently similar to a problem which is exactly solvable. And two is when perturbation term is very less than the exactly solvable part. So under these two conditions, only we can apply approximation exactly solvable part. Under this two condition only we can apply perturbation method or approximation methods. Okay. Fine. So another point I can mention at this point, that why we apply approximation method. For example, in my first example which I take from our daily life in the market, say we all have calculators, even in our mobiles we have calculators, then we can easily calculate using this mobile. But why I do approximation? You remember that by applying approximation method, we can understand how much the approximation affects the exactly solvable or dominating part. This is the main cause behind the approximation method. Similarly, in matrix method, when perturbation is small, sometimes it is required how perturbation affects the exactly solvable part of this matrix. In physics, particularly in magnetism, we still use Van Vleck susceptibility, you know. So Van Vleck susceptibility equation is determined using perturbation method. This method is derived on the basis that external magnetic field is small, or the Zeeman splitting due to external magnetic field is small compared to its full level splitting, and in that case we can use Van Vleck magnetic susceptibility. And also by using this method, perturbation method, when we use Van Vleck susceptibility, it is sometimes required how the Zeeman splitting affects each level, each J level of a magnetic ion, when the magnetic ion is placed in external magnetic field. So we derive the Van Vleck susceptibility equation using perturbation method later. So today I finish the basic understanding of approximation methods, and in my next lecture we advance our knowledge, this knowledge, to quantum mechanics. So till then, goodbye.